What? See? All right, so we're talking about friction. Shh, come back to me. We're talking about friction. And in yesterday's lesson, we were talking about the balanced forces, right? Between the force of friction and the force of you pushing, right? So there was no acceleration. There was no net force on this object. Whereas today, we're going to add more push than just friction. In other words, we've got more force going than what friction can overcome, right? So therefore, this box, in this case, is going to accelerate. It's going to move. So here's example problem number 4 from your textbook. It's on the page that has the number 134. And it says, imagine the force you exerted on the box in example 3 from yesterday is doubled. What is the box's acceleration? And how far will you push it if you push it for 3 seconds? So we have 2 separate problems here, right? 1 question, 2 problems. Let's tackle the first piece as well. What is the box's acceleration? Now, I'm encouraging you. I already pre-wrote this, but I highly encourage you, before you do a problem, you do this. So you know what you've been given, right? So we have the mass from the previous problem that said it was 25 kilograms. The mu was 2.20, the coefficient of friction. We found yesterday in example problem 3 that we were pushing with a force of 49 newtons. So we doubled it and we got 98 newtons. It says that box was moving at 1.0 meters per second. And yesterday the box wasn't accelerating, it was just moving constantly, right? That's how we knew force of friction and the force of pushing were the same, because it wasn't accelerating. It was just keeping a constant speed. And in this case, for the second question, they say the time that you're pushing it for is 3 seconds. We want to know what's the box's acceleration. So here's the only new thing today. You with me? This is the only new something. Are you comfortable that there is actually a force net on this box? There's a net force, right? It is accelerating. You can't accelerate if you don't have force, right? What are the 2 forces in the horizontal direction that are working on this box? The force of your push, right? And friction. Okay, so if we drew the box, right? If friction is pushing this way, what can you tell me about the force that you're pushing? It's going the opposite way, okay. And what else? Has to be bigger, right? Our arrow's got to be longer here for the force of your push. And we know that, again, because this box is accelerating. We cool? So therefore, if I want to calculate the net force on this thing, how would I do that? Like, I'm going to use these 2 forces, but what would I do with them? Okay, so the force of my push minus the force of friction. Now wait, I thought when you look at net force, you have to add all the forces together. Isn't that how you get net force? It is. But it's in the opposite direction, right? Your friction is going the opposite way of your push, so therefore that's why it's negative. Does that make sense? Doesn't mean friction has to be always negative. We've just said that the force of push is positive, so therefore this has to be negative. Does that make sense? Because they're going opposite, we can't simply add them, we have to subtract. Or add the opposite, right? Add a negative something. Are you with me? This, truthfully, honestly, oh my, what do we do here? This is the key piece for today. Okay? We're going to use this in multiple different ways throughout the rest of the period, but this is the key point. When I have motion, right, that I am causing acceleration, there has to be a net force. And in this case, the only 2 forces working in this horizontal plane are friction and the push. Are there other forces working on this thing? There are 2 others. What other forces are working? Gravity, right? Gravity's pulling down, right? And what else? The normal force is pulling up. So why don't we include them in there? They cancel, right? They're a nice force pair that are equal and opposite. We cool? I got like no feedback from you all there. Okay, we're not trying to find forces though, right? This problem we're trying to find acceleration, right? So could I take force and break it into its pieces? Like what two pieces make up forces? Mass and acceleration. So I could say that ma equals the force of my push minus the force of friction. We cool with that? Okay. This is my force push right here, right? That's my FP. That's what we discovered yesterday, right? Okay, so I got that. Do I know the mass? 25, okay, cool. Do I know the force of friction? I don't know it, but can I calculate it? Okay, how do I find force of friction? What's my equation? So we said that it's mu times the normal force. So we could say that ma is equal to the force of the push minus mu times the normal force. But do we know the normal force? We're not given it, right? Okay, we know the normal force is just opposite of gravity, right? They have to be equal. Okay, so can I calculate the force of gravity? How? Mass times the acceleration of gravity, g, right? So then I can change this to ma equals the force of my push minus the mu times mass times gravity. Whew. Do I know all of those pieces? Except for acceleration, right? I know m, I know the force of push, I know the mu, I know the mass, I know the gravity. So we can solve. You could just pop in. I just wanted you to see the progression. Now, I will say you asked about on a test. I always encourage you to write as much, as far as your work goes, on a test as you can. Because I want to be able to follow exactly what you were thinking. That's what I prefer. Because then I could say, oh, Richard, he had exactly the right plan, but he just plucked in the wrong number from you. Well, that's mostly going to be correct. I'll give you most of the points. Does that make sense? Well, we're solving this for a, right? So therefore, pretty easy to do that. I'm just going to divide both sides by m, right? So therefore, a is equal to fp minus mu mg all over m. If you want to be technical, you could even cancel out the two m's, but it's fine. We'll pop them in. So a is equal to, what's my fp? 98, right? Minus, what's my mu? 0.20. What's my mass? 25.0. What's my gravity? 9.80. All divided by 25.0. Just a review on the math, right? Multiply the pieces, subtract, then divide. So therefore, with all this wonderful work, A is equal to 1.96, and we roll back up. How many significant digits should we have here? I got 2 here, 2 there, 2 there, 2 there, 3 there. For this you're talking about? 3.0? Yeah, no, you're right. I should have put 3.0 there. Because that's what it gives you in the textbook. But here we go. So we'll go 2 significant digits. So therefore, how would I round this 1.96? 2.0, it's acceleration. Does acceleration have units? Meters per second squared. Are you with me, my friends? Going back up so you can see it. This is where we began. Because there was acceleration, there has to be a force. So therefore, we know that the force of our push has to be bigger than the force of friction. So we subtract the two to get our net force. We substituted MA for our force. This should be one of those things that came up and woke you up in the middle of the night. Josh, what is Newton's second law? You should be able to tell me. F equals MA. Right, see, I said Josh. You never know which Josh I'm talking to, right? See? Clever. We substituted for frictional force, we substituted the mu normal force. For normal force, we substituted mg. And then we ended up with this lovely equation. Any questions there?
So I thought that the importance of significant digits was when you were looking at your answer. Shouldn't you be more specific? Because in this question, we're using that acceleration. So wouldn't it be better to be more specific than 1.96?
I hear you. Because they're actually going to look for that, they want an answer for this one, I would go ahead and do my rounding there. I hear where you're going because we're going to use it as we continue on. But it's okay. It's okay. It's a good question. We just can't be more precise than our least precise answer. So that's why we go for that. We cool here, guys? All right. So our acceleration is 2.0. Are you comfortable when they ask you how far will you push it if you push for 3 seconds? They want distance, right? They want displacement. So I ask you, if I have an initial velocity, I have a time of 3 seconds, I have an acceleration of 2.0. I want to know how far something travels. Have we learned any equations that we could deal with that? I'll give you a hint. They're over on the board to your right there. Right? These are all of our Chapter 3 acceleration equations that we learned, that I promised you would have to know, right? Because we keep coming back to them. The next piece we're going to do on projectiles uses these same equations. Okay? So, based upon what we have here, if we want to find xf, we got two choices, right? We got the xf equals xi plus vit plus 1/2 at squared. I probably should write these down here since you listening at home can't see these. xf is xi plus vit plus 1/2 at squared. Or I have vf squared equals vi squared plus 2a xf minus xi. Or the simplest equation that acceleration is vf minus vi all over t. But you all got those memorized, right? You know those. We've used these over and over again in the time we've been here. Okay? So my question to you is back to here. If I've got this information, which of these equations do you think that we should use? Again, we want to find distance. How far does this thing travel if you push it for those 3 seconds? The top one. Why did you pick the top one? Okay, we've got one velocity, so we don't have multiple velocities. I would agree with that. We're trying to find distance, which this is already solved for distance, right? So that's helpful. Do I have all the pieces there? I do. What does this second equation not have? Time, right? And we've got time. Time is like the key thing they gave us, right? It said that we push it for 3 seconds. So therefore, there's no way we should use the middle one. And the bottom one just doesn't have enough information. It doesn't give us all we need. We could solve a final velocity, but it wouldn't give us distance. We have to do another equation to find that. Are you with me, my friends? So we're going to use this top equation, xf equals xi plus vit plus 1/2 at squared. Let's plug it in. What is my xi? Because that's one thing we didn't give. Just going to be 0. Are you comfortable? Unless they give you some information, xi is always going to be 0. Because it's your starting point that you're measuring from there. All right? So I'll even put it over here just so you're comfortable. xi is 0 meters. So 0 plus, what's my vi? 1.0. How long are we going for? 3 seconds. Plus, I'll move down here, 0.5 times, what's my a? 2, we just found it, times 3.0 squared. Just to remind you again, order of operations, because I can't tell you how many times I'm helping people and they don't do order of operations correct. Squaring the 3 first, right? Multiply the 3 pieces, multiply the 1 and the 3, and then add them together. So what do we get? How far does this thing travel? Anyone? Anyone? Bueller? Y'all even recognize that if I say that? 12 meters? I'm cool with that. And this actually comes out to be 12 exactly. So there's my answer. You pushed it for 3 seconds with the force that you were giving. It moved 12 meters. A decent distance. Are you with me, my friends? Taking you back to this slide here, this is our key formula for today. The force net is the push minus the friction. If something is just coasting, like if it's just coasting to a stop, are you comfortable there's no push on it? So therefore the force net is just the same as the force of friction, right? So I can solve it out for ma to be equal to the force of friction and solve from there, right? It's only if you're actually pushing on it that you will have that FP force there. Does that make sense? I'm giving you a clue for the first problem you're going to do. So there you go. 5.2, numbers 22 to 25. Walk and wool.